Okay, yeah, it should be live. Let's wait for the audio to appear. It should appear soon. Okay, it's there. Ooh, I'm overdriving. Okay. In this stream, we will take a look at this device. You might be familiar with it if you're following my videos, because I already did something with it. Let me just show you full screen. This video. In this video, I used a sound meter and I installed it in a club. And if the sound was too loud, it was just shutting down the power amplifier, audio amplifier, so there would be no sound anymore. And this would prevent from being too loud and annoying the neighbors and so on. More details in here. So it's been there for 2 years and now this device died. And I will have a look at why it died. Let's switch back to the bench. And so, yeah, how did it work? So what's the symptom? The symptom is that when this, okay, now I see the screen also. This is the receiver. This is the transmitter. This is the receiver, and the receiver should connect automatically should receive the data. The transmitter is sending it over Bluetooth. It has a Bluetooth server. This is a Bluetooth client trying to connect to the Bluetooth server, and this actually controls the power supply. Here the power strip. Here you can plug the power strip, and it can shut it off because the power strip has an internal relay, and you can reset here. But as you can see, when 0 is written here, so this is 0, it means that it's not connected. In this case, it's normal that it's not connected because this one has no power. So let's give it some power. This is micro USB. Let's get some micro USB. Is the sound still working? It's not very loud, but it's working. And I think, no, it's driving fine. So that should be working. So if we drive this is switching on. Let's switch this off. And what I did is I modified this so I can connect the microcontroller on it. It's been quite some time. I don't know all the details of the project anymore. This is why I write documentation and make streams. So it works and nothing is happening. So normally the microcontroller should switch this on, but in this case it doesn't do anything, and I think this is the problem. It doesn't switch it on. We can see what's inside. Yeah, so here we have a microcontroller. This is an STM32F103. Then we have a Bluetooth device. It's an HC05. Yeah, I think it's HC05, which creates the Bluetooth server. And below that, let me up here. This is just a voltage booster because this requires 5 volts. And afterwards, we will see inside here what's happening. So now the issue is it doesn't switch it on. Can we switch it on by hand? Because this doesn't seem to switch on. Maybe here there are no 9 volts anymore. We can test that. The multimeter should be working. Out plus, out minus. 9 volts. Exactly 9 volts. So that's not the issue. The 9 volts are not the issue, at least not on this side. Maybe the cable is broken. Maybe here it got loose. So let's get it doesn't do anything. Or maybe it just doesn't press the button. Let's get this off. Let's get the battery. 9 volt battery. Up. I have one here. I hope it is charged because, so this is a 9 volt battery, but actually it has a LiPo with a boost converter, and I use them to recharge because I don't have any 9 volt charger, but I have micro USB charging. I hope this has still some charge. Red. Let's see. We can still keep the charge connected. Okay, this should have 9 volts. Now can I switch? Okay. Okay, so when I switch this behind here, there's here there's a light sensor to measure the ambient light, and if there's not enough light, it will switch on the screen. You see, it switches on the screen, so power comes in, but it seems the microcontroller doesn't get power. We'll have a look at that. Why doesn't it start? And can we get power from here? Let's try this. I think the code, it's been quite a while, the code periodically tries to start. Yeah, what now? I think we saw it. It simulates the button press, and it periodically tries to get some. Yeah, there you see. It flashed briefly, like it pressed on the button. You see again, flashing. Here. So it tries to press the button, and the idea behind pressing the button is that it keeps it on because this has a timeout. So whenever you switch it on, after 5 minutes, 10 minutes, I don't know, after some time it switches off. And the purpose, there are two purposes to switch on and off. It's to keep the timer, but here, when it doesn't get any measurement, it tries to switch it on by simulating the press and the button press, the power button press. So power works and button press works. Oh, so there's something inside here which is broken. Let's have a look at what is inside. We already took it apart, and let's have a look again. Screwdriver. Let's get a small screwdriver. Can I fit? Yeah, this fits. Okay, the screws are not good anymore. I should have another screwdriver. This one. Generally, it's power supply which fails, but here there is some power course coming in, and the light was going on, so it doesn't seem to be a power supply issue. It's been on for 2 years continuously. I don't know if this electronic is supposed to hold that long. I see even it starts to have some discoloring. This plastic on the UV has this tendency. I don't know. Is it bromide or something like that? Okay, now I need to press this so I can open the device. 1, 2. That's the inside. So what? And here there's a bit of pitching. This is glued. So this is the trim pot to set. Oh, there's even a trim pot as alternative to this one. There's a surface mount trim pot. Here's the microcontroller. This is all the audio amplification. This is the LCD controller. Let's see if the microcontroller gets some power. So we can leave this on. This way it will try to power it all the time. We don't have anything. This is ground and this is power. We see it because the capacitor plus is also connected to that. And this has no power. It tries for a short time. Let's use with the battery, or at least, I do have a power supply. So let's try with the power supply. This is plus, this is, so the plus on the receptacle is the larger one and the minus is it right? This is minus, this is minus, okay. Let's set 9 volts. 120 milliamps should be plenty sufficient, practically. Even if it's just to start, can you see it? Yep. So the 9 volts are on and currently doesn't draw anything. If I press the button, also doesn't draw anything. Is 9 volt coming there? So here there is a power supply issue. Let's connect the ground to it. ground. Let's connect it to ground. So 9 volts, this should be the 9 volt input. Is this 9 volts? No. There are plenty of test points, but I'm not sure if... So the 9 volts, these are going through battery plus, battery minus here. It's going here, so we should see 9 volts here. We don't see any 9 volts here. But this is battery. Why don't we see 9 volts? Do we see 9 volts here? Nope. Okay, I know why. Up, wrong. So switch it off. Wrong leads. Up, up. Now the leads are correct. Here we should see 9 volts. Yep. Here we should see 9 volts. Yep. And if we press on, we see the light draws 10 milliamp. So at least when we press the button, we know it draws 10 milliamp. Now let's try to figure out if the power converter works. 3.5 volts. So yep, 3 volts. This microcontroller gets the 3 volts. But the microcontroller doesn't send any data and doesn't turn on. So there is a bug. Did I dump it? I don't remember if it had readout protection and if I dumped it. I think the microcontroller is dead. So the power seems to work fine. Power goes here, but the microcontroller doesn't start. And I don't see any damage on the microcontroller. We could see on the crystal if there is some activity. This way we know if it tries to start the crystal. But I've never seen a crystal which went bad. I don't know. The issue seems to be somewhere else. Does it try to... What is this? This is probably an op-amp also. Does it try to communicate? This is the LCD data line. So let's try this out. It doesn't, else it would work. So here, what you see, how did I interface it to my microcontroller? Because this is just a display. Well, the microcontroller is sending a stream of bits to this LCD controller, which is right under the LCD, and this is the chip on board under the epoxy blob. And there were some test points. I just put some test points. I remember I cut a trace. This is why I fixed it here. This white wire here. This is because I cut a trace right there. Why did I cut the trace? To figure out which were the digits. Yeah, it's been a while since the video went out. And here we have plenty of electrolytic caps, but none of them seem to be bulged. Here we have tantalum caps, which is also quite an old technology. Well, old. It's not used that much anymore because it's expensive. And multi-layer capacitor. Ceramic capacitors are getting lots of things. This is TP7665. This is very probably the voltage converter, which powers not only the microcontroller, but also the LCD and so on. This uses this as input. We have plenty of transistors, but the power is there. I mean, we see the 3.5 volts, so the microcontroller should switch on. So let's see if there is some activity. Okay, so the LCD works at 5 volts, but there is, I don't see any lot of activity. I should switch on the oscilloscope. Let's try with the oscilloscope. See if there is something. The multimeter is not meant to detect some activity. Meaning I need to start the oscilloscope script. Oscilloscope capture. Let's wait until the oscilloscope is on. Oscilloscope is on. The capture should work. Oscilloscope. Okay. Yeah, this is what it looks like. And let's have a look. So it is slow, but we should see any activity. Switch on. Wrong button. Up. LCD data switch on. It switches the power on. We see it. The oscilloscope. For you, it takes up 2 seconds or so. It takes more than 2 seconds. Can't it connect? Didn't it connect to the oscilloscope? Ah, damn it. No route to host. Are you not connected to the network? No, you were not. Now you are. Let's try again. Now it is connected to the network. Okay. But the image is not refreshing. Okay, let's start again. Why is my screen restarting after every 2 seconds? Ah, the oscilloscope has a bug. It restarts every time it does a capture. It's exactly after 2 seconds, and the 2 seconds are the time I'm using on the thing, so the oscilloscope is buggy. So let's switch that. Menu, not rolling, but yeah, time. That's fine. Auto run, that's working. 1 second. Let's make it shorter. 200 milliseconds. And that should be faster. So, do we see something here? Nope, nothing. The oscilloscope has issues currently. And also, do you see the updates? Is the time right? 1945. Time is also wrong. Let me switch. Let me debug the oscilloscope for a short time. See if it works. Project. Oscilloscope capture. Yeah, image viewer. Let's show it to me. Okay, it doesn't capture. What? I know. I don't have ImageMagick installed. I restalled my computer. Don't I have? No, I don't have ImageMagick installed. Nope. Magic. Yeah, install ImageMagick. Okay, ImageMagick, okay. Means that converting should not work, should now work, and you should see the time is working. Okay, this is fixed. So, why are you displaying crap? This should be running. Okay, now if I put on, it should show 5 volts or 4.5 volts. You are showing nothing. Oh, that's the wrong one. This wasn't the probe. This was the multimeter. This is the probe. Okay, 4.5 volts, but there's no traffic. So it doesn't communicate. It means that the microcontroller has an issue. And there is not a lot I can do for that. I could reburn it. I don't think I've dumped it. This project is so old. Here's definitely the debug port. We could try to read it out. Is there a kill program? Because nothing seems completely broken. It should display something. If it doesn't display something, maybe it has an internal time counter and it knows that after 2 years of being constantly on, it should kill itself. Or maybe it's just that there was a huge X-ray blast which erased the memory from that. That's possible. Let me check my data if I made a backup for that. Let me find a project. Archive projects. Here, no, this is, here we have source code, but this is source code from my device. Yeah, this is source code from my device. I don't think I dumped it. I don't remember having read it. When was the modification? 2000. When was? How could I have named it? This is before this time. Handheld controller, smaller rifle, storm draw, dehumidify this. But it's afterward. When is the video? The video is from 2021-01. 2021-01 sound meter. Okay, there I have it. I'm not showing you all my projects. Some of them are very private. But I still have my backup. Let's see if in the backup there is something inside. If I dumped it, extract here. I don't think I did. It's extracting. Oh, damn it. Datasheet enforcer. No, this is the source code, which is public. Meter, this is the source code, which is public. The other part, pictures, no. Twin bus, it's no. No, that's the tests. Readme. Tank measure, no. I didn't make a backup from that. Could try to connect to it and see if I can speak to it. But do I want to? It seems broken in a theme. It's not something which I can fix. I don't have the firmware, so I wouldn't be able to fix it. Readme is done. Yeah, I wouldn't be able to fix it. Let's see if it starts to crystal. That we can do. So let's continue unscrewing it. Let's power off while we're unscrewing. 1, 2, 3, 4, 5. 1, 2, 3, 4. 4 screws. Let's put them apart. And if not, I mean, I think I've paid something around 20 euros or 15 euros for this device. It's not, it's okay, I can get another one. Okay. There are even some buttons. These are buttons. Capacitors. No buttons. These are buttons to set the levels, the AC. Okay. This is for the contacts for the screen. Here we have a ZBrush strip which conducts just on the Z-axis. These are 2 buttons. This is the light sensor. I think it's cadmium CDS something. So we will need to press the left button, right? Power is left button, yeah. And we will see if there is some signal on the AC, on the crystal. Where is this? Is it enough so it holds itself? Let's check that. No, I have to hold it. So let's switch power on. Power is on. Let's connect here. And I think, yeah, we should put AC, but just increase, because crystal exciter? Crystal circuit doesn't put a lot of voltage. Ah, there is. See the signal? So the microcontroller is working. Kind of. Now it's high. We need to put it in AC. So coupling AC. Okay. Let's try again. It doesn't work. Maybe it's just the crystal dead? Nah, I don't think the crystal is dead. I've never heard about a crystal dying. It tries to do something. We see high, but then we don't see the frequency. But nah, let's try the other way. The other one. Okay, here it does nothing. Maybe it just, there it is. High. We have lots of noise, but it's okay. But there is no activity. But I have no idea how to test crystals. No, I don't think the transistor tester can test crystals. But we see that we don't see any frequency. We see plenty of noise, but we should see an AC wave. Tuck. Milliseconds. Okay, let's try it this way. Up. No, I don't see any frequency. What is this 16 megahertz? Do I have 16 megahertz crystals? We can try to swap it. Now it tries to start it, but it doesn't start. Maybe it can still be that the microcontroller is dead and not the crystal. But it doesn't start the crystal. Do I have... I think if I have him summon this box. Let me put this here. Okay. So 16 megahertz. I do have. Let's switch on the desoldering gun and let's try that. If this doesn't work, then it's gone. Then it's probably the microcontroller, not the crystal. I have plenty of 16 megahertz crystals. Power is off. Oh, I just cut the wire. Not important. I broke the wire. I can still fix it. Let's switch on the soldering iron. Let's wet the sponge. Let's get the solder. This probably don't need anymore. And let's get some pliers. Why do they have an inductor on the outside? The inductor is a DC to DC converter. It's not just an LDO. And they didn't have enough space to put a surface mount inductor. That's weird. Yeah. But it seems to be super efficient. That's good. Good design, at least for that. So, the soldering gun should be warm enough. It has plenty of cable mingling, so okay. Will be loud. 1. Oops. 2. Now I should be able to lift it. If I did it correctly, almost correctly. One side wiggles, the other side doesn't wiggle. Let's wiggle the other side. Let's try again that. I don't want it to. I don't want to damage it too much. Up. So up. So this is 16. Yeah, it's written on there. Whoop. Can it focus on it? And here it's written 16 megahertz. Okay, let's put a new one in. Let's solder it, bend the leads so it doesn't go back down. One, two. Cut the leads while holding them, else they will just fly everywhere. Particularly in the eye, they have an eye detector, eyeball detector. Let's put this back in, so it doesn't get stuck. Up, let's try again and see if the excitation works. So power on. I don't need flux. Button is here. Button on, and I don't see the display, but I can still check. No, there's still no AC waveform. We see try to start it. No AC waveform. Yeah, I think the microcontroller is dead. Well, not completely. It tries to start it. The firmware might be dead. Meh. Not recoverable without the firmware itself. And I'm sure that the firmware is available nowhere. Ah, I also broke the LCD. Ah, that's a shame. Let me fix it, even if I won't use this thing anymore. My OCD is triggering me. That's one thing, and let's also fix this. That's the other. Soldering iron is already hot. Let's cut the power while we do it. One and two. That's done. Let's put everything back in. So the screen goes here, the button is already there. If it doesn't display anything, then I declare this microcontroller dead. And we will come to the next step, because if you looked at the thumbnail, you probably might have guessed what my solution to this issue is. Okay, the button is the wrong way around and the cable broke again. Come on, button, this way. Up. Maybe it knows that it's out of calibration after some usage. It's a clever device, actually. I don't know what happened to this device. Power seems okay. Why don't you close correctly? Because the screen is not inside here. These are the small screws. Screw them, but not too tight first. One. And yeah, the screws put pressure between the LCD pads and the screen, the zebra strip. And the zebra strip didn't look bad, else there should have been some screen activity, also some tearing, but there was nothing. So I don't think the zebra strip is an issue. And we also didn't see any data coming to the chip. So it's not the screen the issue. Okay. This is back on. We have 1, 2, 3, 4, and here is the fourth screw. Let's put it in. Okay, that's the fourth screw. Let's switch power on. If we switch it on, we see tries 1000 millivolts, and yeah, this thing is dead. Okay, and I couldn't fix it. But this is the first. So this is probably one of the cheapest sound level meter you can use, but at least it seems to be halfway decent, and it seems to be quite some reliable measurements. And this is called, I think, GM1351. I'm pretty sure this is it. Do we see it written here? It was written on the box. It was written on the back here, but it's not there anymore because I didn't use it, so I removed it. It's not written there. It's not written on the PCB. But yeah, just look for GM1351. It's one of the cheapest sound level meter you can find on AliExpress or favorite site. I'm sure it's even on Amazon. And this is the next cheap one. So this is pretty old. This is the new one. And looking at the color and looking at the button, I think they're the same manufacturer who did it. So I'm pretty sure that and this is the GM1352, so it's very probably the next one. Even the marking looks similar. Here they have a specification on the back. You see the trim pot again, but instead of 9 volts, they now have 3 times 1.5 volts, which is better. Better because it means that they're expecting 4.5 volts or 5 volts and not 9 volts anymore, so I don't need to boost the voltage. This is good. What do we do with this? Let's close it and let's put it in the archive. Do I want to? Maybe I still have. Come on, go in, stupid cable. Why don't you want to go in? The other way around, maybe? No, it was this way. It was there in the beginning, so the glue should have not moved too much. I didn't heat it up. Let's move a bit of glue. Up. 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 And we have only 3 screws. I think I lost one because I see 4 screw holes. Where is the last one? One, two. I'm sure there must be a last one. 3, and it can't be very far away. Here, 4. So this device can be put to the archive. Won't work anymore. And I'm surely pressing on a fit. So that's gone. This up goes in the trash. This I don't need anymore. Let's have a look. Let's switch off the soldering iron. The sound enforcer we can put on the side. Let's switch off the oscilloscope. You don't need it anymore for now. So you have a better view. Up. Next device is the GM1352. So it's very probably... does it work? Because I know I bought it because I gave away my sound meter, but I didn't try it out. And I bought my... Why do I am looking for the sound meter now, the project? Well, two things. First, the first one died last week in the club. They're not using it anymore, but they still said it died. So I should do something about it, or I wanted to do something about it. And for my kettle project, which I want to make silent, I need to have some measurements. I need to know how loud it is and how more silent I can make it. This is why I need a sound meter. So this works. Yeah, batteries are empty. That's fine. I know it works. 1, 2, 3 batteries. Up. Let's have a look inside. 4 screws again. One. Let's see if they changed everything or if it's the same thing. 2. Because of the trim pot, I don't know. Let's see. This is just a note for myself. Oh, actually I could put the note here. Yeah, this one, to continue the timeout, see it has a 10-minute timeout. This is what the note says. And if I want to reset the timeout, I have to 10-minute hold reset time button. Hold? Hold. If I press on hold, it resets the time. Okay. Oh. Actually, it's almost the same thing. No. Let's open the thing again because it's too good to be true. Oh. They actually it looks so similar. It's the same manufacturer, and here you see the name GM1352 right there in small. So I have to open this again. Damn it! Why did I close it? Just to look how similar it is. We even have the same DC to DC converter. Or is it a DC? This needs higher voltages. Because here we have an LDO. This is for the 3.3 volt here. And so let's have a look at the differences. Maybe we could even fix it. You see how similar it looks? The 3 ICs, 1, 2, 3 with a trim pot. What is this? KS993. It's switch. I don't know what it is. We have the chip on blob. We have the same microcontroller with the same pads. What they removed, what they made easier is actually this chip is not there anymore. I don't know what this chip is. This is an 46C001. What is 46C01? It's a TI chip. TI 46C01. LM46C01. DHS, it's an op amp. Okay. Yeah, here we also see the same chip, and here they laser that chip. This is, oh, and here we have, so this 46C01 has been replaced with the GM1688. Can I zoom? Yes, yeah, it doesn't focus anymore. Yeah. So these two chips replace the TI part, the 46C01, because we have two of them, and this is now an this is an Xperia HEF 40528T, and this is probably the same chip here, or an equivalent. We have the same, yeah, TP60. So this is DC to DC converter. I don't know how many rails it has. We even have this inductor, which is still on it. We still have this inductor. So it's the, I think they made copy paste and they just simplified a lot the circuit for the 9 volt, and they use 5 volt instead with this part. This is very probably an LDO for 3.3 volts. Yeah, it's micro semi. I see the logo 6208. 08. I would have that 6233 for 3.3 volts, but we can test it with our multimeter. So the multimeter minus up goes here, and we switch this on. This is now on. Multimeter plus. Normally this is ground. This is ground 0 volts. This should be output. This should be input. Input here we should have. We don't have. Okay, that's not the input. Okay, that's weird. That's not the output. It doesn't measure anything because ground is not connected. Here we should have 3.7 volts. That's fine. That's why it complains about the measurements. And here, so here we should have the input. That's the output, 3.3 volts. And this should be the input, 3.4 volts. And this is 3.6 volts. So they very probably have a diode. Here, this is the diode, which drops the current, or which drops the voltage. We see 3.4 volts, 343. And we have the same right here. So this is the input, 3.4 volts. And here we have 3.3 volt output. It manages. It's an LDO, but LDO, it's a very low dropout. It has just 0.1 dropout. This is good. The chip here is able to manage to measure the current, to measure the voltage, and to know that the battery is running low. So I think this, very probably here we have a voltage divider between this and this. This puts it to ground, and here we have the voltage which is read out by the ADC. This would be my guess. No, that's not a correct guess. 2.7 volts. And if we increase the voltage, we probably see the 2.7 volts, which is increasing. Can we cheat that? We could. Let's remove the batteries and let's test out with 4 volts, and let's increase it slowly. Up. So ground plus we have 4 volts. We can throw a bit more, and if we measure here, yeah, 2.7 volts. So we have a voltage divider. If we increase this, you see it increases also. So here, this is very often how you do it. You have a voltage divider because this is only able to have 3.2 volt input measurements, and this goes up to 5 volts. So we have a voltage divider, and then this voltage divider goes to this point. I think this point is to connect to ground or not to make the voltage divider work, because when you are not switched on, you don't want the voltage divider to be on, draining the battery constantly. So for that, you have an external or internal, very often external, NMOS. This is probably this one. It might be this one. That's, well, 3.8 volts, so it's still drawing some current. So is it even the same microcontroller? The microcontroller is, oh, this is so small. I need some glasses, and where do I have my binoculars? This. Some light. I can already see better. BB10 F8G. Is it the same here? This is an ST SIL F330. It's not the same. It has also not the same form factor. Oh, it does have the same form factor, but it doesn't have the same amount of pads, does it? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No, it has the same. Does it have another marking? Is this BB10? Let me check with. So this is SIL Silicon Labs F330. That's the one on the old one. SIL is very probably for Silicon Labs F330. That's probably one of their series. Yeah, Silicon Labs. This is an 8051. Makes sense. It's cheap. Small form factor. And the 80 probably means it's also an 8051 on this one. But it's written. So let me check. Is it 8 or is it B? BB10 FAG. It's not exactly the same one. It's very probably an alternative. BB10 FAG. Let's have a look. BB10 F8G. It's still one of the Silicon Labs. Let me switch the screen so you can see what I'm doing. Screen, full screen here. That's the old one. F330, so SIL Silicon Labs, and this is an 8051. This is the new one. It's an 8-bit microcontroller. This is also an 8-bit microcontroller. Yep, 8-bit microcontroller, but they are not equivalent. So I cannot copy the one firmware from the other one. What is based? This is just, what does it say? Sample kit by now, technical docs. I have to enable the things. Technical doc. Family library. I want the data sheet. Just the data sheet here. Data sheet. Busy Bee. BB, Busy Bee. I've never worked with this library, with this family. Oh, it's also an 8051. Okay. So very inexpensive. They probably make it also. But I'm not sure they make it pin compatible. Let's have a look at the pin definition. This is the wrong one. This is 20. Yeah, we have 5. Let's have a look at this technical doc. Is it pin compatible? Is this one just end of life? Datasheet, pin layout, pin out. No, it's not pin compatible. You see, here we have ground. On the other one, it's here. So it is not pin. Oh no, it's not the same one. Sorry, wrong chip. No. there's only one QFN 20. The QFN where you have, this is weird. QFN where you have pads in the corners. Else it is pin compatible. P01, no, it's not pin compatible. P00 ground, P00 ground, VDD. And then we have clock. And afterwards we have P0D, P16, P16. It is kind of pin compatible. No, not here. You have ground again, which is not on this side. It is very similar. It is not pin compatible, but it's very, very similar. And probably because it's the same core, it's the same thing. Does it support? Let's have a look at the features it has. So this, you can go get lost. So we have a better comparison, side to side, side by side. We have an ADC that's here, triggered, here, pipeline, 5V Torrent IO, this is good. 12-bit ADC, this is just an 8-bit ADC, woohoo. That's already better, so it's not completely compatible. 4 timers, here we have supply voltage, but this BZB family seems to be nice. 64 general purpose counters, that's fine. We have UART, we have SPI, but this has more. UART, SPI, Assembers, PCA. I don't know what PCA stands for. Programming code array. Meh. And then we have 4 timers. What is PCA? Programmable count array. Oh, okay. This probably also has it. And it is very, very similar, but it's not the same, and I don't think that they are code compatible. I would be very surprised. But the code didn't change a lot, and they just used, this is probably less expensive or still available. Why did they change? Here we have also again PCA, programmable counter array. This has even 3 channels. Woohoo. Yeah, QFN6. So it's not completely pin compatible. I don't think it is. It is code compatible, but the interface is the same. So it's not exactly the same chip. Either way, if this is dead, this is. If the other one, the 31, is dead, I don't want to spend too much time. It's not an expensive device. It's 15 euros. This one is 15 euros. I wouldn't want to revive this. Let's try with this one. And what is good is what I saw. So 1, 2, 3. Let's put the screws here for later. What I saw is that this interface is the same, but not only that. If you look, let me switch back to the bench. Up. If you look here, we have again data, write, and CS, which are also. Can I show it? Yeah, here. LCD data, LCD CS, and probably the last one is LCC VR for write. So they are very probably using the same chip. And is it on? Yeah, it is still on. Now let's push on hold. Now if we have a look with the oscilloscope, so I need to switch on the oscilloscope for you again. I don't have any stream deck where I can control everything. That would be nice though, to have some kind of stream deck here. Maybe I will build some at some point. Yeah, that would be nice. Yeah, and I could build one. Yeah, no, okay. Here we have, we don't have any crystal anymore. It uses the internal oscillator. It has an internal oscillator. I mean, they pretty much all have internal oscillators. What? So core 25 maximum frequency. Here, internal 24 megahertz. So it's not 16 megahertz anymore, it's 24.5 megahertz. And it uses the internal one. It doesn't need to be very precise timing. So I cannot measure the oscillator and show you what it looks like. What I can show you is that here should be some traffic. Up. Let's switch. This is not AC anymore. No, here, this. Not ground. It's so slow when it's taking pictures. DC. And if we look at the data, and if we don't make it up 2 volts, that should be fine. And now if we make the trigger normal, 1 volt should be fine. Yep, you see the data. Now, does it have the same segments? Or do we have to reverse the segments again? Here we have the chip select. So, yep, you see the chip select takes almost the same time than this thing. So we can use SPI again. And right, what was that? That's a lot of data. How did it work? Because this is data. This is also data. And that's a lot more data. This is to tell if it's a command or if it's data. So it's probably high for data and low for commands. And this is the actual data. So the same trick I used here, I could put, and what's the voltage? What is the voltage? 3.4 volts. That's good. That it means that I can use any microcontroller I would like. I don't have to use a 5-volt tolerant microcontroller, which I did for this one because the levels were at 4.5 volts. Now I could use, for example, a microcontroller which is not 5 volts tolerance. And I have the 3 points, and I just need one more point. It's the press button. It's probably this one or this one. No, but maybe not. Auto. Okay, if I press on it, let's test. It's still on. Test, press. Yeah, you see? If I press, it goes to ground. So I can simulate the button press by connecting to pad 1. Pad 2 is probably the lights or shut down. Let me press on the other button. Okay, I don't know what 2 is. But at least 1 is the button press for the hold signal. Because did they make? I don't think they make. It looks very similar, right? I don't know how the other screen looks like, but this is a lot. It's a lot easier to interface. I could try to get the same codes and connect this to it. Not exactly. Yeah, I could. I just have to not put 5 volts, but only 9 volts. Or I could just not provide the voltage here. I don't remember the pinout for that, but I very probably wrote it down. And else I can just have a look here. Which cable does what? With here, I mean the old one. So let's have a look and see if this works. And if I made it correctly, this USB, I will have a look. Let's connect it to my hub. And let's check what it says over USB. I think it also sends the measurement over USB. Okay. So what I did, sorry, the camera was too zoomed. I just connected this microcontroller over USB, and let's check if there is some data up. I think is screen. Yep. Pico. Let's increase it so you can read something. Pico.com. We don't care about the baud rate because this is USB, dev, TTY, USB, ACM, not USB, ACM 0. No values, trying to power it. Yep. Tries to continue on. So we could try to connect this microcontroller to the new device and solder the pins on there. So let's disconnect this. Let's switch on the soldering iron again and let's connect some cables. And we can try to figure out which pin does what. Actually, I could just take this as it is. The battery, I just have not to connect it, but the rest seems to be the same. And this is what I'll do. I'll just salvage this connector. And here we have even the button press, which is the white. And we could... yeah, we'd have to change this thing as the voltage booster. Can I switch it back to low? I mean, here we have a high voltage regulator. I think it supports up to 3 volts, up to 6 volts probably, even more. So we could just decrease the voltage regulator from that and use this again. Some tweezers. Okay. So one after the other. This is, let's put some solder. Oh, we have no power. This is good. Let's put some solder blobs on data. And they're not too cheap, you see. The pads are gold. ENIAC at least. 1, 2, and 3. So this white one is CS. Let's write it down before I forget it. White is equal CS. Then we have green, which is right. Green is right. We have blue, which is data. Blue is equal to data. Then we have red, which is plus. Here now it's 5 volts, but we'll red. But I'll decrease it to, here it's 9 volts, but I'll decrease it to 5 volts, so VCC. Black is ground. I need to connect that. We always need a reference. Black is ground. And we have the other white, which is the button. White is equal button. And let's put also the pin numbers. Do I care now? I don't see it through. I don't care about the pin numbers. So green. This is green. Now we have data, which is blue. Still leave this one on. Then we have long white, long black, and long red. Ah, I need two buttons. Although I couldn't. Yeah, I don't have enough. Previously, the power button was also the button to reset the timeout. Now it doesn't work anymore. Now it's a the hold button is the hold button is the reset timer. So what do? Do I connect it to the power button so I can switch it on, and then I have to switch it on every 10 minutes? Or do I use the do I switch it on manually and then it can keep it awake? But I don't have enough cables. Yeah, I don't have enough cables on the 6-pin header to do both at the same time. For now, we don't care. For now, what's important is to switch this low up. Oh, I still have the logo on that. Bench up. For now, we will just turn this pot so it goes down to 5 volts. Do I have a small screwdriver? Flat, please. Oh, none of these flats. Yeah, flat screwdriver. This is the multimeter probe. I don't know what ground here is. Yeah. There's ground. Probe. This should be 9 volts, and let's decrease it. So now we're completely bypassing. I could connect it directly. Yeah, no, I don't want to remove this microcontroller yet, this board yet. I'll just leave the board, we never know. So I don't have to modify it, and we go down to... What's the input? The input is 5 volts, and you can still have an output which is 5 volts also, but not lower, right? Lower? This is a buck boost converter. 4.8 volts. Ah, no, that's because of the LED, of the diode. 5 volts is fine. I'm sure it can handle 5 volts. It can handle 4.5 volts. So 5 volts is for its... Oh, we can actually drop it to 4.8 volts, the minimum. Let's drop it to the minimum, 4.8 volts. Okay, so here we have the output. Now we can try to solder everything as it was. Red is plus, so nothing is connected, okay. Red is plus. This one moved. It's always a pain when you have two cables. Okay, then we have ground. Are you seeing what I'm doing? Yeah, you are. The button, I still don't know which button I want to make it go to. Okay. And then we have the two. So white is CS. White is CS. Okay. Then I need right, which is the blue. Blue is data, green is right. Right. I don't remember how I did the decoding. I think I used SPI, but then I use 2 SPI channels. Oh, I used Mozy and Miso? Nah, I don't know. I don't know how I did it in my code, because here we have a high-low. Maybe it's just fast enough. And data. And now if we connect it, it tries to switch it on. It can switch it on, but if I press on, it switches on, and that's all it does. Did I break something? What happened? No, it's not broken. This works. But this should be completely passive. This should be completely passive. Why are you... Okay, this is weird. This is off. Now I connect this. And I can't... Ah. Do I also switch power on and off? No. Here we see on the DMM, we see 4.8 volts, which is currently on there. The hell? Is this device actually working? Well, let me try. It's just that my code is broken and it was interfering. No, it's not. Because we tried it also just with a battery on this one and it didn't work. But let's, just to be sure, let's try it again. Switch on. Oh, it doesn't switch on at all. Even the light is not going on anymore. Because there's no power in this battery, and that's very probably the case. Yep, no, still, this is broken. And here, is it because it's too high voltage? Let's try. So this is not on. Let's switch the voltage on. Power on. Okay, power off. Power off. Let's make it 4.5 volts. 4.5, it says that it's full. That's okay. 4.8, this is also what's injecting. 4.8 switches on. The cables, this should be completely passive. Let's switch this off. Switch this on. I can switch this off. It should still... Okay. And now if I switch this on, 4.8 volts, can't switch it on, that's normal. Why? Let's have a look at the oscilloscope. Because it has not this... No, it has the same ground. So let's have a look. White is CS. CS still works. Should be this long. CS works. Here, this should be right. Right has no activity at all anymore. This should be data. Data has activity. Am I sending something on right? Right has no activity anymore. Why? Is my code broken? Let's disconnect this wire. Okay, the right wire is disconnected. If I switch now on, I need to provide power. Power. Okay. The right does something. It holds it low. Why are you doing that? What is my code doing? So my code is... That's my code. No, this is my code. Let me show you my code. Up. Application. Here I probably define no. I have a library especially for that. Okay. Lib. Yep, sensor here. On off CS SPI. Okay. So here, why can't I select? This is weird. Why don't you allow me to select? What is happening with Chrome? Is it Chrome? No, I can't select. Can I select elsewhere? I can't select on this page. Why can't I select text on this page? I have no idea. So that's chip select. That's on off. Here power on. Control through an N-channel MOSFET simulating button press. Connect to D-pad on the text side. Okay. So this can be a power button control through an N-channel simulating button press. Okay, this is why I have a MOSFET in the thing. But I could actually just pull low 5 volts. Why are you treating this? Okay, you're just not showing me that you're selecting something. So using SPI, why? Here segments. Okay, here I've mapped the segments. I hope that it's the same. I just hope it's the same. It doesn't have to be, we will see. But currently, the issue is that write does something. But I'm not using SPI2. It's using data. Here. Yeah, connect clock. Write is clock. It is very repetitive. This is the clock date. This is the clock data. The hell? This is not regular at all. This is not a clock line. You don't see it because it's on the oscilloscope, but why am I treating it as clock? And also it should be only an input. This is definitely not a clock line. Connect to clock and MOSI to data. Okay, that's now master output, slave input. We are the slave. Did I write some text? I didn't write. This is from 2020. This is 3 years old. Dev group peer connection. Here, this treats it as clock. Why do you treat it as clock? Was it clock on the other one? And this was to test. So how I did is I injected also as master to figure out what the display was. But clock? I could put a logic analyzer on it and we could check, but let me set up the bit pattern. So configure GPIO for an on-off button, SPI peripheral, set clock as input, set mode, input float, okay. And here I should configure it as slave mode, set slave mode. We will handle the chip select so we know when a transmitter starts, stops. Yes, there is a C for that, NSS high. Set CS high to disable receive. Why would I want to disable receive? We have a CS line. Why don't I use the CS line? Why don't I use the hardware CS line? SPI ISR, XTIO, here. Entertainment chip selected, deselected. Now I know why we use it, because when it's high, we know it's the end of a frame, and when it's the end of a frame, then I can read the data. Flag received when this is high, and then I disable it by hand. And when it gets low, and it's probably fast. Is it fast enough? Well, it did work on the previous one. That's decode, that's toggle, okay. But it's definitely not a clock. Do I need to put a logic analyzer on it? I think I need to. So let's it's not a clock. Let's put a logic analyzer to it. But why also? Why, when you're connecting it, are you driving it low? Theoretically, you should be an input. Disconnected to ground, disconnected to ground. Let's check. This, okay, 0 volts. And when I have a weak pull-up, it should be high. So what if I connect it to... This cable come out. What if I connect it to 4.5 volts? It is 5 volt tolerant, yep. So here we have 4.5 volts, and if I connect this, it tries to pull it low. Why are you trying to pull this signal low? Microcontroller? This is not my code. Yep, the microcontroller doesn't like it at all. Is the microcontroller working? Did I break it? Let's test it. I did break it. I did break the microcontroller because I shorted one pin. You can't break that fast. Can you? Did I break the microcontroller? Oh yes, I did. It's getting warm. This is not good. Let's try just to disconnect the power supply. Up and disconnect the earth. Maybe this makes it easier. No. Yep, I did break the microcontroller. Okay. Yeah, I definitely broke the microcontroller. It's getting warm. And it's blinking this light. So I did something wrong. But is this still working though? Up. Up. I need to disconnect this. It doesn't draw. Okay. Damn it. I also broke this microcontroller. I fed back the 5 volts back in this microcontroller. Damn it. Ta-da! I broke everything. Let's disconnect this and let's see if it recovers. No, I didn't. That's good. Should be. It says it's 5 volt tolerant, so even if there should nothing have big should have happened. So okay, this still works. Lucky. Let's solder back the wires and let's put a logic analyzer to it. So switch on, switch off this. We have white should be CS. Then green should be right. Yep. And blue should be data. But actually, if it's SPI, then you need a clock. You need a clock if it's SPI. So let's try if this works again. Let me switch back to the bench. Up. Yep, this works. Now we can put a logic analyzer on this part and test if it works. So let's switch this off. This microcontroller is dead. And the project was dead. So this goes here. It's a bit of a shame, but yeah. Up. Could make it a bit different also. But yeah, I have to write that this is dead. I'll write it after. I'll write. Let's write it now, else I'll forget that it's dead. Let's try again. How do I want to test it and how do you want to show it to you? I know how. I will use the other power supply. Oh, can you still use this power supply? So you can also actually see the measurements. So this up now 3.3 volts. 3.3 volts up. One goes to ground, the other goes to 3.3 volts. Up. Up. And if I switch on, it triggers the limit, and there's no way that my microcontroller draws more than 120 milliamps. This is not a hefty microcontroller. Let's see how much it can draw. Yep, there's a short somewhere. Yep. There is a short. I think the microcontroller is dead because it's getting warm. If it would be a short in the LCU, then the microcontroller wouldn't be getting warm. So I broke the microcontroller. And because it's an STM32, they cost a lot of money now. Although maybe price is regulating. Let's try to desolder it. Whoop. Okay, let's try to remove the chip with hot air. And if I remove the chip with hot air and it still has a short, then it's not the fault of the microcontroller, but I'm pretty sure it is. Up. Gone. Up. Switch this off. 3 volts. 0 volts, switch on. Yep, See, it doesn't draw any current anymore. It draws just enough for the LED to go on 1 microamp, so this microcontroller is dead. Now we know. I'll write on the box that the MCU is missing, and I'll write here, I'll do it afterwards, that this is also dead. Not this, what you don't see. This one is the old sound meter, the GM1351. Now we need a logic analyzer. Let me get my logic analyzer. Where's my probes box? Probes. Here, up. So it's a Sealy Logic clone. It's not a real Sealy Logic, but I'm also not using the Sealy software, so who cares? Oh, actually this doesn't work anymore. No, it works, it's just outdated, I think. Does it? I think this software doesn't work anymore. I didn't try it since I reinstalled. Let's see. We will see. So we need USB Type B cable. USB Type B. Plug it to my... Ah, I know why the LED is blinking, because my USB hub has a current limit. So my USB hub was preventing it from drawing more than 500 milliamp, which is good. Let me first try if this is detected. I think Sigrok scan. Sigrok CLI scan. Oh, it detected it. Okay. Okay. That's a good sign. So we need one ground, which is... I have to beep it out because I don't see anything. One, so which pin is ground? I would expect to be 1. Normally I put ground on pin 1. Yep, ground is on pin 1. So I did a good job. Ground is pin 1. Oh, now that I have more cables, I actually can solder more wires, because I don't have to use this microcontroller anymore. I can use another one since this one is broken. I broke it. And the other one probably 1. We will see some traffic. 2 and let's put 4, 3, 4. It looks, no, the red one. Where's the red one going? Let's put on all channels. Yep. These the right colors. And why is one missing? Ah, here. This one is not connected. This is channel 3 is not connected. All the other ones are connected. Let's put power back. Here is the power clamp. The right way around. Power here. Power here. And power for that 5 volts. Let's switch it on. It still works. Let's now switch Sigrok on. Pulse view. Pulse view. Pulse view. Okay. Let me show you full screen. And pulse view. 500, yeah, 1 mega samples, that's fine. Let's see if we detect anything. Yep. We clearly have some traffic. Here we have the CS, here we don't have any, so this is battery. So I only need 1, 2, 4, 5, 6, I think. This is VCC, this is CS, this looks like data, and this is VR, this one is VR, the clock. It's not a clock. Let's put 1 megahertz. Let's scan on CS and let's put a trigger of 5%. Let's capture a frame, and we have a frame. We can put at 10 megahertz. We still have plenty. 20 megahertz. 500 kilo. I just want one frame. You see these glitches here? So VR is the data. Okay, now wait, what? How are the changes always? Okay, the changes are always when this is high. High change, high change, high change. Okay, so this is a clock. This is just not a periodic clock. If I have some SPI decoding, SPI hub clock is VR. It is VR. We have data. Chip select is select. CS polarity active low. Clock polarity. What do I know what the clock polarity is? It is valid when it is low, so clock polarity is probably high. I never know the combination clock polarity, clock phase. This seems to be accurate. No, it's not, because it should match. This is okay. No, it could be accurate. It is low while it is going high. No, while it's going low. When it's going low, you fetch the data, because when you're going high, then I change the data. So actually you could fetch it when I'm going low, high, and any rising. Yeah, we see that during any edge, the data is always the same. So here we have SPI, and here we have the data. We have plenty of 0 zeros at the end. Why are you sending 0 zeros? And my code says how many bytes? The frame, 17 bytes. No, yeah, 17 bytes. Do we have 17 bytes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19. We have 19. No, 17. I miscounted. So it's 17. It seems to be very similar. Yeah. I see byte 0, 1, 2, 3, 4, and 5 are the ones which were used. If we look at here, 0, 1, 2, 3, 4, 5. And the last bit, we don't care, probably it's always the same. Segment F, all other bits can be set to any value. Yeah. So 0 to 6, we have 7 bytes, so it's not exactly the same. 0, 1, 2, 3, 4, 5, 6. Maybe this is just a remaining if I change the polarity. No. And polarity change doesn't seem to be the right thing to do. So in SPI, we know that it will change data after the rising edge. So when it goes, so it is when it is rising, and when it goes low, it is stable. So we could actually, since it's stable the both way around, if we change the polarity, the phase, it should say the same values. It says the same values. Clock polarity is not important, but the data seems to be decoded better with clock polarity, clock phase at 0. You see that's a bit weird, but the data is the same. Yep. Data is the same. Now, are the digits the same one? That I don't know. I probably not, because it has a battery indicator. But here we have, yep. I think, so what I could do is now, instead of having this contraption with a Bluetooth device, I could just put an ESP32 on there with Bluetooth. So the not the S2, but an ESP32 or an ESP32F3 or a C3 could do the SPI decoding, and we can really use this as clock. Now, why did my chip pull it low? I don't know. And here we can still use, did I ever use the SPI from ESP? I don't know. Yeah, I don't know. It will be a pain to decode the segments. I can still inject, yeah, this is what I'll probably do. I'll hold the chip on the reset and inject my segments like I did for the previous one. Either I cut the trace. I could cut the trace and then put it back on. Would it be easier? It's the data trace. I could cut the data trace and then fix it like I did for the previous one. And then just have the microcontroller. So this, let me put this. That's the data trace. I could cut it and then fix it again. Or just solder from here to here to fix it. And then while cutting it, I can flip the single bits as slave. It would be my slave output. That's probably how I'll do it if it doesn't decode correctly, which I'm pretty sure it will not decode correctly. But this is software. So software, I still need to, I'll probably do it on an ESP now. And I need to set up the ESP and so on. That's not fast. It always takes me a bit of time. So I will not do it in front of you. But I'll use this one. And once this is done, I'll probably also publish the code. I know it's just SPI decoding. You just have to map the bits. And then you can still use the same code which decodes the digits. So there we have it. We know how to interface this. We will probably boot an ESP, so then we can provide with 5 volt directly. ESP can interface the data and can send it over Wi-Fi or over Bluetooth. That's the next part. And if it's small enough, I can actually put, no, I don't want, I still want it to be battery operated. So I'll put probably the ESP here. You can plug over, yeah, here there will be the wires going through. There's enough space for 5 wires going through here, 6 wires, 7 wires, because I need to simulate the button press. For 7 wires going through here, oh, 7 wires, it's still a lot. I can make a hole here where I can plug the cable then, going through here, where I can control the buttons, and then I'll control with an ESP and not with this thing anymore. And this, the controller would probably still be able to use it. It's just this sound level meter is dead, but c'est la vie. It did its job. And once I finish that, I'll probably also, yeah, like always, publish my source code library for the GM1352. So that's it for today. We know everything. The rest is software programming, which I find boring, and I won't stream. Probably just stream the result when it's done. But for now, the stream is done. enjoy the rest of your day. Bye bye.